Welcome to all of you in the lecture series of Maxwell relation. In our previous video, we discussed about the fundamental concepts of Maxwell relations and as well as the thermodynamics square, which is useful to write down the fundamental differential equations and the Maxwell relations. Now in this video, we are going to discuss about the derivation of Maxwell relation. The question is, by using fundamental differential equation du is equal to T ds minus P dv, we have to prove this first Maxwell relation. For derivation, we write down the given differential equation as equation number 1, du is equal to T ds minus P dv. Now here in equation 1, the first term is ds. Therefore, at constant entropy, ds is equal to 0. That is, when the entropy is constant, the differentiation of constant term is always 0. Therefore, ds is equal to 0. And therefore, equation 1 implies that du is equal to this term t into 0, it becomes 0, is equal to negative p into dv. Now, just by cross multiplication, we can write, when we divide this dv here, this d becomes dabba, that is partial differentiation of u with respect to partial differentiation of volume keeping entropy constant is equal to negative p. That is, the differentiation of internal energy with respect to is a partial, therefore we write on the partial differentiation. Now for further step, we have to adopt the hint from this. Here we obtain the expression of p, therefore we have to differentiate equation 2 with respect to s, keeping this volume constant. That is, we have to differentiate equation number 2 with respect to s, keeping volume constant. Then we can write dabba by dabba s, dabba u by dabba v, keeping entropy constant, and overall it is volume constant. Then we will write dabba dabba square u into dabba s dabba v, keeping entropy and volume constant, which is equal to, now with negative sign, dabba p by dabba s, keeping volume constant. We caption as equation number 3. Now for the next part of derivation, we have to adopt the hint from here. Here dv. Therefore we can consider that at constant volume, dv is equal to 0. And if we substitute this condition in equation 1, we obtain du is equal to T ds. This term becomes 0. Now again, just by cross multiplication or we can write dabba u by dabba s at constant volume is equal to t. Equation number 4. We obtain equation 4 with the expression of t. Again, we have to adopt the hint from here. That is, we have to differentiate the t with respect to v, keeping entropy constant. Therefore, equation 4 we can differentiate with respect to v, keeping entropy constant. Then we can write dabba by dabba v, dabba u by dabba s, volume constant, and overall entropy constant. That is, dabba dabba square u dabba v dabba s, volume entropy constant, and the right hand side becomes dabba t by dabba v at constant entropy. Equation number 5. Now on comparing equation 3 and 5, we observe that the left hand side is equal. Therefore we can write the right hand side is also equal. Therefore on comparing equation 3 and 5, we can write dabba p by dabba s, keeping volume constant with negative sign, is equal to dabba t by dabba v at constant entropy, and that we have to prove.